Okay, well, I'll preface this in saying that I attended a few of the other lectures of this series, and there were tutorials how to actually do things, how to program things. And I saw the series going on, and I thought, well, you know, in a control room, the accelerators run by EPICS as well, but we use a different way to interface with EPICS than some of the other people, especially the users. For example, well, the users' beamlines have like 200 motors. We don't have a single motor except for scrapers. We have mostly set points and readbacks, things for which we don't have to wait. We developed our way of doing things back in 1994 when we were commissioning the Linac and the PAR and then the booster and the storage ring. We started off running shell scripts and then realized, you know, somebody from Jefferson Lab came and gave a lecture on tcltk, and we thought, well, this is the thing to do. It has a very clean syntax, and we can probably launch commands from that shell. So tcltk was a big thing in the middle 90s. Not so much now. People learn Python if they're new to the world of controlling things with EPICS. This is kind of I take this as a record of what has been done in a control room since 1995 and how we progressed. And so far, we haven't seen any. We haven't found anything that tcltk in combination with our tools, SDDS and our SDDS compliant EPICS tool can do. Of course, we don't. As I said, we don't have motors, and I wouldn't know how to start with that. So the outline is what is SDDS, in case you're not familiar with it, and how we use it. Then the scripting language tcltk, and then I'll go into the examples of applications. We have a few hundreds of applications. I just put a few up. Things as simple in this operations as setting up the storage magnets. We set up other things in, when we start up from a shutdown. I just use the storage magnets application because I'm more familiar with it. Then there's orbit correction, the correction of the orbit of the storage ring, using the BPMs and the correctors, and an inverse matrix that connects the two. And we have various beam experiments, measurements that we use EPICS for, that is launched by a simple button press by a tcltk GUI. Another application is generalized feedback, which I hadn't prepared any slides, but I let it be known that we can create a generalized feedback that can be configured to whatever transfer line that you want, or other PVs that have a dependence on another PV. And finally, knobs. It's always good to have some empirical adjustments of something in a control room. So you have you gang a lot of PVs together and apply up and down arrows to make the ganged PVs move up or down by according to some array of coefficients. The software I'm going to describe is found in our web pages. That's been in place for about 15 years. Okay. Well, we use data files. Obviously, we use data files in operation. Actually, it has a primary a central role in operations. We know EPICS holds live data, so we could have an MEDM screen, some display that shows the single PVs updating every second or every tenth of a second or what have you. That provides feedback for an operator to see what's going on. We can also type in a value singly in those MEDM displays. However, to do something more complicated, we have to record all this data, and we record it in a file rather than the resident memory of a large interface. We'd like to use EPICS data by reading it and saving it, maybe post-processing and sending it back, sending the values back to EPICS to accomplish something in particular. So in order to to organize our efforts better, it would be good if we had a file protocol for all the values. This not only goes for EPICS data, but also other kinds of data, configuration data, even simulation data, which I'll mention later. So we'd like to have in our group and in our division data saved using the same simple protocol. So our applications, on all of our applications, I repeat myself at this point, that all the data, the experimental data, and also configuration setting, which is another way, it's a form of data, are all stored in files. And I use these software tools as filters to build larger and more complicated processes. So we follow the aspects of modularity, that is, make small tools so you can make bigger things with them. Reusability, that is, the example of feedback. If I develop the feedback for the first transfer line at APS, LTP, it's called LTP, then I realized it could be made for all the other transfer line, but just changing a few names here and there. So we use a configuration file that lists the name that the tool will use to do the feedback. And also, anything that anybody writes can be used by somebody else. The AOP group reuses each other's libraries extensively. And hopefully we can attract users outside of our group for this. So this is a pictorial of how the control room work is done. Suppose if we wanted to start up a sector or the whole ring, well, an operator sits at a computer and has to do something there. In our case, it'll be launching a procedure or opening a window that has a button that says start, or maybe something more complex in which you have to set parameters and then you press start. Inside of this procedure on scene are the EPICS command line tool that we all know, ca put, ca get. Those are run directly from, say, a shell. And then we have some more complex EPICS tools that, for example, that can set a list of values to a list of PVs. And these lists will be taken from our file server, and the EPICS compliant tools can also write data to a file, and which can then be post-processed and giving other data that are more readable for us. So I'll come back to this later. Everything that is done in control room is done using scripts or GUIs. And line by line, there are some internal variables that are specific to the scripting language. But in the end, we have to communicate with EPICS using data files. And OK. So let's describe what SDDS is. The acronym is Self-Describing Data Set. So this is a file that contains data whose header explains what the data means. I repeat myself, we need a protocol for a standardized way to store and access data. And we already have about 100 tools, 100 programs that uses this file protocol. We call it tools because they're small, the small objects that read a file and make another file. And you can combine many of the files, many of the tools together in pipes so that you can start with one file and transform it internally by a first tool, and then transform it again with a second tool, and then get something different. That's useful for doing statistics and post-processing. So here's the diagram. The data source could be EPICS or could be even a scope trace. You know, all scopes have their own format, so we have to go through a conversion program that we write for, say, a scope, and then becomes SDDS data. And now we use SDDS toolkit programs to do something, say, with the scope data, and then we can plot it. It comes out either as a printout or a plot. This is what I mean by human readable output. Here's an example. Here are a list of toolkit functions that was written by Mike Borland. By the way, many of the slides, many of this information is taken from a previous lecture given by Mike Borland or some web page written by him and Bob Soliday, and possibly some former programmers of our group. So obviously the most important tool is the so-called SDDS plot. This is to display data. It has like about 100 command line arguments. It's actually pretty flexible, and we've seen them in publications around the world. It's interesting to see that. We also have a contour plot display, so we can view 3D data in that way. We can print out as a formatted text, like a Fortran type printout. We can summarize the data sets, say take the sum of a column or take the average, whatever. Data processing and equation evaluation refers to making a new quantity from an old one. Say if you have the energy of a beam, you can convert that to the magnetic field of something that is needed for the magnet. So you have to enter a coefficient and then do a multiplication and get new data from that. Data filtering, we use it a lot on experimental data. We want an outlier removal is important to throw out the data that would affect the average or the statistics of what we're seeking. We have fitting and smoothing. Matrix operation, yes. A data file could be, instead of a few columns, could be a big block of data. Each column would be a column of a matrix, and each row of the data would be the row of the matrix. It'd be nice to do some linear algebra, which we do. So an inverse, the singular value decomposition, is one application that we use extensively for beam steering at APS. Cross-referencing refers to having two separate files that has a common column between them, and you want to join the data in between them. So they may be unsorted or whatever. Cross-referencing will take the data from a second file and join it up with the first file and make a third file. We use that quite extensively. It is a little complicated, and it's necessary to use these toolkits to make this cross-referencing. I couldn't imagine how you can make a single-purpose program after another with cross-referencing. You need a toolkit to do cross-referencing. FFTs is used for noise analysis of our beam and other things that can be read quickly at the APS. This is nothing new. The MATLAB and other scripts, the first complicated thing they install is FFT, so we did the same too. We can also do deconvolution of a signal with that. Now these are general tools that act on generic data. It doesn't matter whether the data comes from EPICS or come from a simulation code or something you just type in one row at a time. The next set of tools are those that connect to EPICS. EPICS is communicated in a manifold way. You probably want to read 1,000 PVs at a time, so tools that use just one will be insufficient, obviously, unusable. So we collect data from EPICS. We collect about 50,000 PVs, and we log them at a fixed time interval. We even have the flexibility of logging more important PVs faster than others. Say, temperatures don't have to be logged that quickly, so we log them every, say, 64 seconds, whereas the beam current, which is one of the prime key parameters of the storage ring, is logged every minute, every second, I should say. So we have lists of PVs that are logged at different time intervals. Okay. Event-driven data logging. Well, this would be collecting your beam orbit when something bad happens. So we define, using SDDS file, a set of conditions that would cause this data logging to occur. This usually applies when you have to data log things very quickly. And if we were to do it for all of time, it'll be too much. So we trigger on an event. It actually makes it easier for the user to find the event as well. We log the alarms. This is good. There's already an EPICS extension called the alarm handler, which is used for immediate action by the operator. So they would act based on how their own alarm handler is logged. At the same time, we need to log the alarms for posterity, so a physicist could look over, pore over the details, and this is what this is for. It goes along with the data logging. We can do an n-dimensional experiment. What I mean by experiment is a scan of a PV, which then affects physically other PVs, other control quantities in the ring or in the accelerator. So this is an experiment where you'd vary something along one direction and collect data as you go along. That's one dimension. You can extend that to n dimensions, so you can vary two things separately, independently, and collect data and post-process the resulting data to find out what is going on. The save and restore of EPICS data, well, that's probably the most important thing we use in the control room. We want to restore configuration after a shutdown. So we restore files that may contain thousands of process variables for magnets, for BPM settings, other things, Cherenkov detector settings, for example. I already mentioned generalized feedback control, and we can actually do optimization, online optimization of things. We define a set of variables that the optimizer will scan in some simplex, using the simplex method, and use a script to read back what the optimal value is. Some value, and they search n-dimensional space, a simplex, until they find an optimum and reports the result. We use that often for injection optimization. Okay, now SDDS, I already said a few things about it. An SDDS file consists, it is important that every data element has a name. That's basically it. We do not refer to a data as which column it's in that file. It has to have a name. So any tools that use SDDS files will have as arguments the name of the column that you want, or the data that you want to do things with, never the number of the column. Okay, so that necessitates a header. So there's going to be a nameless type header. For those who know Fortran, Fortran invented this nameless type of entering diverse type of data. We have a header that defines the name of a parameter, say, and the type, and maybe the units. The parameter is associated with one table, so there's only one instance of a parameter for each table. In this case, I quickly found the smallest SDDS file that could fit in transparency here. So in this case, we have a table of just two values of kickers. I was doing a kicker experiment, and one of the parameters of a file was the pause between readings. I guess this is a file used to configure an experiment with the kickers. The kickers' names are given as a column here. The next column is a lower limit, which is a numerical value, and the next column is an upper limit, and the numerical value. So when an SDDS Optimize reads this, or some other program reads this, it will interpret these columns as being those named by lower limit and upper limit. And these names will be configured to mean something in the program. Okay, so here's the table itself. It consists of a row, the number of rows, and then the actual data, so that the SDDS libraries know when to stop reading because of the number of rows. The other use of SDDS I mentioned in passing before is if we use the file protocol for everything that we do in our work, computational work, then it's easy to marry the two sides, the simulations and optimization in our offices with what's going on in the control room. For example, last January we had problems injecting. So Mike Borland did some optimization of sextuple settings for the optics of the storage ring. He ran it on, I don't know, some cluster in Argonne that you had thousands of cores. And he finally got a solution of better configuration of sextuples, especially near where the aperture is small and so on. So this was different configuration than what we presently have. So he put this data in a SDDS file, which you already know how to use because we use SDDS files for setting up magnets all the time. So that allowed us to communicate, to marry between the two worlds, simulation, optimization, and operations. So now I'll go over what is TCL. It is a scripting language. The TCL stands for Tool Command Language. Well, it was invented in the early 90s, I believe. What I like about it, there's a lot of features that could be described. You can go to a web page, this page, that gives 100 features of tcltk using computer science language. I read them and I decided to only put in the features that I understood so that I can explain it to you. It has a simple syntax, actually. There's very few special characters. There are data structures. I guess I did not put it here. There's the data is kind of free. There's no typing. Data doesn't have to be long, double, or whatever. It's all handled internally. And in addition, the data structures could be a single variable, could be a list, could be a list of lists. It's nested, and you can have arrays as well. They have the usual control structures. That's all the other programming language. For example, if, for each, and while. It has a built-in event-driven programming, and I believe this is built in, whereas other scripting languages would have to have it added in after the first few versions of it. There is a graphical user interface toolkit called TK that's seen elsewhere, but it actually was designed for TCL. So they were born at the same time, I believe. You can launch it from your terminal if you have Linux using TCL shell, tclsh, or our own version that has some extensions called OAG tclch. Okay, so suppose that you launch tclch on your terminal. Then how to use a variable? Well, you have variables. You can define a variable, set phase, say 180. Okay, that's an accelerator type thing. The syntax has no equal signs like you have in other programming language. It's deemed redundant. What else would you have to say after set variables? You'd have a number. You wouldn't need an equal sign. There's no other options that would follow. And the line ends there. I don't know if there's a semicolon. I forgot to check. I never use semicolons. I don't know if there's semicolons here. It probably is. Yes, there is. Yes, I just thought of one. And if you want to know what the value of the variable is, just write puts phase, and on the terminal get 180 written back. Lists. A list is formed by the same as a variable. Set a variable name, a new variable name. It could be an old one, could be a new one. And then you put a group of values around curly braces. 1, 2, 3. That's as simple. So there's special operators that can work on lists as well. I didn't make a list of those operators here. But if you want to know what the A is, you just type puts $A, and then you'll get 1, 2, 3 back at you in the terminal. While there are procedures, like all scripting languages, you'd have to have a procedure to modularize your process. So suppose I want to procedure is defined as follows. Firstly, there's the word pros, space, the procedure name. Could be anything, could even be a character like question mark. Anything is allowed. And then a variable name that will be in the invoking command. And you expect in the invoking command, I forgot to write it down, you'd say calculate square, space 4, and then you'll get a return 16. So you put in a placeholder for the value x, and then the x will be used internally here as a local variable. The return command will return the value in this expression. The square brackets here is an element of the syntax, which means run what's inside here and return the value. EXPR expression is an internal mathematics calculator function inside of TCL. So it runs as you expect, x star x. It has a Fortran-like syntax. Will give you the square of the value. If you were to run a command calculate square plus a variable that is undefined, well, you get an error, and TCL will tell you have an error because this line gives the expectation that you need to have a value representing x, or a number that is a number representing x. Here's a fun example that I'll explain more of the syntax using this example. Here we have, it's going to make a recipe from random words. This part sets a list. A is going to be a list, and the list will be the text strings. 3 eggs. By the way, this is also a list. It's an element of the list. 3 space eggs is an element, including the space. An apple, a pound of garlic, a pumpkin, 20 marshmallows. The list has a length of 5. So that's characteristics of a list. It has a length and has elements. The same thing too. B, I defined them with also having 5, C having 5, D having 5 elements. So the idea is to take a random element of each of those lists and concatenate them together to make a fake recipe. Here at the, I see. Here I show you the example in which the procedure is question mark. Like I said before, you can define a procedure name with any text, even a strange character like question mark. So now question mark appearing in the text somewhere will invoke this procedure and will have its first argument replaced as L. So if you have question mark, say A, if you call it question mark A like I did here, question mark A, it's invoked. So it'll take the list A and put it everywhere where there's a capital L. So starting deep inside here, this list length command will return number 5. You need a $sign in front of L to expand the list. So you get number 5. And that is multiplied with a function, an internal function called random number between 0 and 1. So you get a random number times 5. And you take the integer portion of it, so you get a number between either 0, 1, 2, 3, 4. Not allowed 5. So then this expression will return a number either 0, 1, 2, 3, 4. This command lindex takes the index of the list L. So if you have index 0, this will return the 0th element of L, in this case 3 eggs. The index starts counting at 0. So in this case, you have question mark $A, you'll get 1 random element here. The same thing is done for B, C, and D. So this is, how do you run it? Well, you save all of these lines into a file, recipe.tcl. I use the extension, the suffix tcl, so I remind myself that it contains tcl commands. Okay, so we launch a tcl shell, and you run the command source. It's used in C shell. Just a source, a file name will simply run anything in there. So we had procedure definitions. So the procedure definitions are now existing in your current interactive terminal. So call recipe once, and the recipe, if you remember, returns a text quotation, takes something, some calculation, some more text, some calculation, and so on. So that's why you have take 20 marshmallows, cut in small pieces, top with raisins, so far so good, and then serve with spinach, which is not so good. You try it again, because we have a random number generator. You take an apple and bury it in the ground for 3 months, top with parsley, serve with rice. That's fun. I sent this to my kids to show them something about programming. They were not too impressed. They thought it was crazy. Why would anybody want a recipe like that? Okay, so that's an example to show how tcl works in the simplest form. There's lists, there's a return command, there's a square bracket to invoke a procedure. There's other things. You can run external commands. It would go with, the first word would be exec, and then the command. The command would be anything that you type in on a Unix terminal. So like if you run a simulation program elegant, you say exec elegant, and all the arguments that follow. In this case, everybody knows ca get command. So you can have a exec ca get. I don't think I wrote it right, but this is a dipole process variable for the current, dipole current process variable. -n is so that you return only the number. So in combination with the set command, you say set I dipole, whatever, 450, whatever the value is returned by CAGET. So that's an example of how to use an external command in tcl. Catching error codes, whenever, if somebody makes a mistake, like would calculate squares with something that is not a value, tcl will complain about an error. But if you're running it as part of a big code, you have to pass this error code along through all the levels of the procedures they may have. So it's important to catch errors, the error codes, and do it in an appropriate way. I'll show a semi-example later. We use it extensively in all of our software, especially that our software is used in operations, so it needs to have high reliability, and it's used by many people as well. So you cannot trust everybody to enter the right number in an entry box. Say if you enter a string instead of a value and a value is expected, then there'll be an error. So we have to have a way of handling these, gracefully handle these error conditions. Rejects, well, it's an internal feature of tcl, and apparently it won some sort of an award of how it's implemented because it's implemented effectively. Reject is a Unix command or a C command or a Perl command. I don't remember its origin, but it's used in string manipulations. We manipulate a lot of strings in operations to manipulate names of PVs and names of things. And that comes in handy, especially after interpreting something that is returned from the operating system. There is some file input-output in tcl. We use some of it only for the simplest of cases. For when we deal with complex data files, we use SDDS toolkits. And the tcl variables itself don't touch the data. We just read a file name, we transform it using a SDDS toolkit, and get another output file, and send it to the network file system. There's sockets communications. I realized we had them all along. We've been interfacing with HP instruments using sockets for a while. We have an instrument from 1994. The vector signal analyzer is communicated with sockets. And it's amazing that that instrument still works after 15 years. It's no longer supported, but we can still do socket communication with it. Events, I'm referring to mouse clicks when a variable, internal variable is updated, when somebody types something in an entry box, presses garbage return, then there are some procedures that can be set up to have tcl run another procedure whenever a keystroke is typed. There's extension available for tcl. That only means some additional commands that you can use inside tcl, not part of the original tcl. People are free to add whatever commands they want to make it look like a tcl command. So we have the PV package for channel access. That was written back in 96, 95 by Bob Daly of the controls group. It hasn't changed a bit since then, and it's still as useful as it was then. Bob Soliday is maintaining it for now. And we have the SDDS package for writing tcl data to and from SDDS files directly. Like I said, we normally, for very complex SDDS files, we wouldn't use it. But say if we have a SDDS file that is used to configure the way an interface looks like selecting the bunch patterns. You know, when we select a bunch pattern for the injection script, that comes from an SDDS file. And there's all the other tcl variables that depend on it. So we use the SDDS package to make that communication. Okay, example of syntax of the PV package. Again, this will work inside of a tcl shell, not a C shell. So you start off with the word PV, and you give one command, in this case linking, a tcl variable with an actual PV name. So this is run, and the commands that would follow will actually put values to the PV or set values to the variables. But first you have to establish a link between a tcl variable that you invent right there on the spot and a PV name. The PV name has to be a real one. Or you can, instead of a single name, you can put a list of names. This is an example that we use for our top-up script. We have a list of about 15 tcl variables and 15 PV names. Okay. And the second word, as I said, it's a command to link, to unlink, to get values, to put values, and also to monitor values. These others I'm not familiar with. There's a variation of these put, get. The W indicates await. That is, the command is blocking until all the interactions on the internet is done, and you actually have the value ready at the moment. Otherwise, if you just use that, then, well, you'd have to write in a special code later to make sure that things have been completed. It's not as convenient, so we use get W and put W in all of our software. And, okay, so here's an example. Oh, did I already do this one? Okay, here's an example how to use it in a code, okay? In a code, this is inside somewhere. So you first have PV link W, and you want to link the PV with the beam current. And then you have the next command, get W, and you refer to the label. This kind of, it's not only a tickle variable, it's also kind of a label. So this indicates to actually make a communication with EPICS and put the value of the PV in a tickle variable as soon as it's invoked. So in here, the if statement contains $, the tickle variable. So at this point, the value is updated and is compared with, say, a target current. And in this is an example of an if structure that I threw in there just because I didn't have a chance to explain an if structure. So if this condition is met, then you can run another procedure, inject more beam. Here's a more complex example of a PV package using monitors. Okay, I'm not sure if I'll succeed in explaining it correctly. What you see here is the link W command, PV link. You want to link 4 variables, and they're defined as this. There's square brackets list. Whatever follows the list command will be a list. Previously, I had a list of curly braces 1, 2, 3. An alternative way to make a list is to use a square bracket command list and then the elements that follows. So these are tickle variables in the code, and these are the PVs. You probably recognize these as PVs. So this command will link this variable with the corresponding PV. Next complication is that as a way of introduction of arrays, you can have an array of a variable. So just like in Fortran, I guess, you can have a single name, a single string representing the array, and then an index 1, 2, 3, whatever. You can have an index of a string. You can have a string as part of an array. So an array is simply a list of objects associated with variables, and you refer to it by any string value. The 1, 2 in this case doesn't actually have numerical value. It has just a string value. So in this case, we're connecting an array, BPX1, BPXY1, APX1, because sector is defined as 1. So you can have variable substitution inside of this list command. So the way UMON works is you type the word PV and then UMON. I don't remember what it means. Can't tell you now. But as soon as this sets up a monitor for this tickle variable, and this curly brace here is an argument of UMON, which is a script to execute whenever the IOC signals the UMON process that its value changed. So when a value of this PV changed, effectively the variable is updated using the script set this $, the same variable name. I don't know exactly what the mechanism, why we have to repeat this, but that's the way it is. And I give you that as an example of how to use monitor in a PV package. Monitor obviously is used whenever a value changes infrequently, but you still want to know when it changes. The alternative is polling, that is, read the value very quickly for all times and then act on it whenever it changes internally in your code. UMON is a more efficient process using the network to tell you when, and EPICS to tell you when a value changes. Now, I mentioned before that it was important to catch errors. So this is the same code as before, but with the catch statements. So that's all I'm going to say. I won't go through every single part of this. Actually, okay. Here we have about, I don't know if this is accurate, we have a lot of GUIs that use the PV package. We have, I give an example and I describe briefly what they do. Experiment Designer. That is a way to do experiments by changing a variable and checking to see what happens to the readback values that you want to detect. PV Monitor allows you to set, we have that for the radiation monitors in the control room. If a radiation monitor, of which you have about 35, exceeds some value, say the minor alarm, then you want to stop injection by ourselves rather than using the ASIS system. So the PV monitor could be configured to do something as a result of a value changing. This was actually the idea of Steve Christensen. He proposed that and we created in a day. We have a steering software. This is changing the correctors around in a straight section so that the beam orbit is moved to where the user wants to. And we also have an optimization where the correctors near a straight section is changed until an intensity detector in a beamline is maximized. SR Bunch Train is a tool we use for injection various patterns. And as I said, it's configured by SDDS files. You just pick what pattern you want, and a lot of things are configured because some other PVs around the ring needs to change based on how many bunches we have. We can do scanning of the RF voltage and determine the energy aperture from that. That's a physics machine studies application. RF phase sliders. This is a GUI that has buttons, left or right, to slide a button, slide the phase of some RF equipment by whatever degrees you enter. Tickle knobs are used in, like I mentioned before, tickle knob is buttons, plus or minus, in which you gang a list of PVs that are naturally associated with each other, but with coefficients. So we can have a knob for, I'll give you examples later at the end of the slide. I realize I have that, so I can go into more details then. And PV package is used in other libraries, which are called by the GUIs. Now, I talked about tickle, now TK. Some of you may already know TK because it exists in other scripting languages. It's basically a windowing toolkit. It creates and manipulates widgets in a window, and a widget could be a button, an entry box, a label, a scroll bar. Could even be tabs, like we see on our a regular Firefox browser tabs. There are tabs in toolkits. Yes, the fancy elements are edited as extensions. Quite a lot of extensions for TK, and it is launched with Wish, Windows Shell, or OAG Wish, our version. And there's more in this wiki help page. We have built a set of TK calls. The primitive TK calls, we wrote wrappers around them so that our APS GUIs have the same look and feels. We enforce everybody in our group to use the standard sets of TK calls for APS, so we all have the same sort of look. So it looks like this. So we have a widget, APS button, for example, the widget name, and then the options for the button. Many of the options are the parent of, you can have widgets within other widgets, so there's nesting involved. And you can place the widget, you can pack the widget one corner or the other. There's options for that. I'm not going to give a tutorial on how to use TK. It's quite involved. And I'm just saying that we have it and we created something, library out of it. For those who want to learn the APS widgets, I have these 3 next slides. a demo script of how to do widgets. If you run this script here, demo script, you actually get a live window in which you can change data in the entry box, select a file based on some combo. These has command support. So if you have a SDDS file here, you can run a command on the SDDS file, like SDDS plot or what have you. You have the disable button. You can run this and read the code and see how this has been done inside the code. I just read the code. It's easy enough to learn how these things to modify for your own widget. So these are example widgets of entry boxes in the entry box tab. The next one is button widgets. You can have a radio button. Well, this is probably nothing new, really. There's been a lot of tcltk, a lot of toolkits that have been created since '95, and they all have basically the same thing: radio buttons, whether to select one thing or another, or check buttons, whether to select one or more things, with all or none as an option. And also a read back of which one was chosen, I think. And a command button to launch. We have a lot of command buttons on our interface. A button has a label saying start this, and then something will start in the background. Here are others. We can have combo boxes, which we use for selecting the bunch patterns for injection. So we get a list of predetermined things. Selecting each one may cause a script to run. Okay, another important thing is some computer languages have commands that have arguments that are position dependent. So if you have one command, the first argument has to be, say, a length, and the second command has to be a time or something like that. So that's positional dependence of arguments. We'd like to have our software written so that we're not dependent on position. Just like we like to have names for the SDDS columns, we like to have names for the argument. So this is how we make names. It's a tag value pairs that actually is used even in latex. It was developed like 10 years ago. So we have a tag value pair arrangement of arguments. So we'd have something like this. You'd invoke a procedure like this, my APS commands, dash variable 1 with value 1. So you intend to have variable 1, an internal variable to that procedure to get the value of 1, of val 1, and so on for other variables. You can switch these things around, and as long as the pairs are, keep their integrity, you'll have the right value assigned to the right variable. And this is how it's done. You have your procedure here. Here you put args, which the args is everything that follows in this line. This args will be read by our procedure called APS parse arguments. It assumes that you have args value and will parse them according to what has hyphens in front. So var1 has a hyphen in front, so it'll return internally, it'll create a variable called var1 with the correct value from this invoking command. So if you were to put puts $var1, you'll get value 1. And puts var2, $val2 will give you val2. So all of our procedures have this command, at least, to handle tag value pairs. Because we have arguments that could be 20 arguments long. Because we do complicated things, we have to keep track of those arguments this way. So coming back to what we do here. We have the tools launched from tcltk. So I changed the label here. So we have a procedure where we just launch something, and each row has either a regular tcl command or a launching command. The launching command could be an SDDS tool or an EPICS tool. So we could launch, say, a CA get command, communicate with EPICS. It could launch SDDS monitor command, which is communicate with EPICS and uses data and produces data, or just a regular SDDS tool to do post-processing inside of here. Okay, here this may be slightly out of order, but I decided to put a slide to show the 3 ways. This is like the Spanish Inquisition sketch. I thought of 3 ways, but it didn't turn into be 4. From EPICS, with EPICS from TCL. Okay, you can use the PV extension package, which I explained. So PVW, put W dipole main, that's how you communicate. You put a value of 450 to a process variable that has been previously linked to that. The next, the next way to communicate with EPICS is an external command line interface. CA put, that same thing, same PV for the dipole, 450. We're going to have a more sophisticated command than CA put. CA put can only do one value at a time, one PV at a time. Mike Borland created this about 15 years ago, vectorized put. That is, he used arguments, this is a C program, he used arguments that will develop a whole array of similar looking process variables plus some repeated value, for example. So the dash list would have a string value in general. If you have many strings, then you concatenate them and it's supposed to make a PV. But if you have a number that changes, then you have to use the dash range equals begin equals 1, end equals 40. So this will create a list of 40. It will multiply your list by 40, inserting a value of 1 after the S for 1, a value of 2 after the S for the second one, and so on. And then this is all appended with a common PV, a common string that will make the PV for a skew quadrupole in a ring. So we actually use these sort of things. We want to set all skew quadrupoles, 40 of them, to 0.1 amps. So this vectorized command is shorter than having to write out 40 CA put commands. And also there's an option of delta. You want to make changes from the present value. So first this command will read what's presently in EPICS, calculate what is necessary using 0.1 and delta, and add 0.1. So this will, having delta has not only a put command, but also a read command. We can use the APS extension library. Bob Soliday took whatever was in that C code and duplicated in a TCL code. It's quite a long code. I looked at it yesterday while preparing this. It has the same arguments, can do the same thing. The difference is that there's an APS CA put. This is a TCL procedure, not an external procedure. The reason we'd want to have internal rather than external, all of these external procedure EPICS tools go through the opening of the channel. There's a lot of busy work done before you can actually change a value. You have to establish a network channel, and that takes some milliseconds. You actually do what you want to do, read or write. That takes microseconds, and then you close the channel. Because the IOC has limited resources, you have to open, close, and you have to close after you open it. So if this is in a loop running very fast, you could overwhelm. You can overwhelm the network and the IOC if you keep opening and closing the same channel over and over again. This library call only opens the first time, and if there's a loop, and then it keeps the channel open. If there's a loop, then all it needs to do is to make a short communication with the PVs, and then once the TCL application closes, then the channels close automatically. So we use APS CA put, CAV put when we have a lot of network activity. And again, we can launch SDDS compliant toolkit to communicate with EPICS. So SDDS CASR means channel access, save, restore. Yeah, that's correct. I was just thinking that maybe it was wrong. So you provide a file, maybe a file with 10,000 values, control names, PV names in one column, and value string in the other column. And if you put restore, well, that will actually do the restore function of channel access, save, and restore. Otherwise, you can use a save command. In that case, you'd have to have two files, one that specifies which PVs you want to communicate with, and the second file which specifies in which will be written the values of those PVs. You can have a SDDS monitor which reads PVs at regular intervals. So you make a list of PVs you're interested in, just a string column with the name control names. And this would be the output file in which all the results will be written, 1 row per time interval. And here you'd specify the time interval and the length of the duration of the monitoring. Control law is actually a feedback command. I took the control law name from one of the elementary books, control law, U equals KX type of control law. What happens in that case, K is a matrix. The matrix, by virtue of it being an SDDS file, everything is named. So if the columns are named from the PV that you want to control, then all the information is known. You have an inverse matrix, you have the PV names, and you also have to supply a string column for the actuator names. So everything could be, all the information to configure a feedback, a slow feedback, is contained in one SDDS file. And that, we did this in 1994, one of the first EPICS tools. The first EPICS tool we wrote was monitor. The second one was control law, within a week of each other. And that was when we were commissioning the PAR. Obviously, we have the normal feedback control values like intervals and gain and so on. So in summary, the one that you choose to communicate with EPICS depends on the situation. Okay. This is a lecture. It's an hour, but I want to finish. It'll probably take 20 more minutes. This is for posterity. This is recorded, and you could visit the YouTube channel whenever. So if you get tired of it, you can come back to it. So here's an example of a procedure run in the operation, starting up the storage magnets. It's actually, to make it foolproof, we have to do many steps and check that each step is done correctly and give progress reports to the operators who are seeing these steps being scrolled down. They don't see everything but just the summary or the name of the steps are scrolled off. Okay, so when we start up a machine, we want to turn on the magnets. Then maybe you have to cycle the magnets. And then maybe the final touches to the magnets, you'll have to give a final current set points to all the magnets. And also, there's going to have to be some dialog boxes that is presented to the user whenever something goes wrong. But that, I won't explain that now. It's all done internally. So this procedure, well, I guess I already said that. We need the parts that involve EPICS is the configure command to the power supply IOCs. A cycling requires a lower limit, a higher limit of the power supply current, the time it takes for ramping, the number of cycles to do, and finally the final value. These are actually PVs that live in the IOC, and we have to calculate them based on configuration files and then send all those PVs to the IOCs. Then the next EPICS command is just the on command to all the power supplies, and you have to wait for completion. Then there's a command to start the conditioning. That's a command in the IOCs. We have to wait for completion and send the final values. So this is the application from which this procedure is launched from. This whole application is called the Storage Ring PEM interface. It's the instance of the PEM Procedure Execution Manager for the storage ring. There's a similar one for Booster, PAR, LINAC. I actually don't know all of them very well, just know the storage ring one. So when you invoke this, you get a list of procedures that you may want. There's a scroll bar indicating how long the list is, and up double sector is a procedure you want. So you go down here, you enable, there's an enable button to prevent accidental pressing of the start button, execute button. You enable this and you can execute. There's also some options, semi-automatic, manual, and manual means that you have to acknowledge every single step. When you press execute, this window pops up, the initialization of the procedure. And this is custom made for this particular up sector. So as part of the library, this initialization window pops up. It has You can select which sectors you want. That becomes TCL variables. Select which family of family of magnets, and select which archive. These are SDDS files that, if you select, will be used to compose the standardization configuration file that goes to the IOCs. So all the internal steps are done with SDDS files that you may never see. Maybe they're put in a temp directory, and they'll be deleted afterwards, but they all use SDDS files. And that's it. You press OK and wait. Look at all the steps go on. I don't have a movie of that. So that is a procedure that's run once. We could have, beam physicists would want to run experiments. Wouldn't want to run them during a run. An experiment is a scan of one or more control variables. So you can either write in a TCL script a loop, a for each loop, and you can do CA get or CAV put, CAV get commands, a put command and a get command, and put the values in the file. It could be as simple as that. We actually do that. It takes 5 minutes if we want to do something quick. But if it's an experiment that we know that we're going to be doing many times in the future, we want to make it a little more formal. So we can use an SDDS experiment tool, which comes with a configuration file describing with nameless commands all the control variables that you want to change and the readback variables that you want to monitor. We use that for the dispersion and chromaticity measurement. The experiment designer is for a very complex situation that needs scripts to run between each step. I'll show you examples of these. I'm not sure which example I'm showing. Oh, experiment designer. Okay. The experiment designer has a large interface with many tabs. There's a tab that defines the process variables that you want to scan. You can have many of them scanning all in one go. So you have multiple PVs that would just scale with each other as you're doing a scan. You have buttons to add process variables. In this case, this was a scraper experiment. This is a PV for scraper position and some limits. You have to specify limits for an experiment. You can even add equation and parameters. It could be very complex, and I could not think of a complex example to give here, and I think it would be too complex to show. CY has a lot of them for the PAR. Next, you have initialization. These are basically scripts that you would like to run to prepare the experiment. And the execution design, what happens at each step. So the first thing you want to happen is a change to the variables that you specified in the first tab. And then you may have some scripts that helps post-process what's happening. Maybe helps wait things out until something's finished. Or maybe to do some adjustments during each of the steps. So, so that's how TCL can be used to communicate with EPICS. That's probably one of the most complicated things we can do. The other TCL applications, I wanted to show orbit correction as an example of modularity. Orbit correction in general consists of changing a lot of correctors around the ring so that the orbit everywhere is reduced at the same time. There's a physical relationship between each corrector and a BPM. We call it a response matrix. We have a model for that. We do an inversion of that matrix so that if we know how much error there are at each BPM, we multiply the vector of BPMs with the matrix, and you get values of how much the correctors have to change. And we repeat that over and over again. This is simply the launcher. We already have the inverse matrix. This is simply the launcher. When you press the start button, the orbit correction will start. The rest of the stuff are auxiliary processes that make sure that nothing goes wrong during correction. For example, you can correct the orbit all you want, but if there's no beam in a machine, the BPMs read garbage and you're correcting on garbage. So there has to be some checks on whether the conditions are valid. We have some of these tabs used to define the validity of the conditions. And we learned this pretty soon during commissioning that such things were required. The next tool here is the orbit correction configuration. This is a set of widgets that, okay, this does not communicate with EPICS. This just communicates with files. This is how we define which BPMs are good, which are bad, which ones we'd like to use in orbit correction. There's also a tab that tells us, that allows us to select which correctors we want. Some correctors are bad, so we'd have to make sure we don't use them. Once all the correctors and BPMs are selected, then an inverse matrix can be calculated using some of these buttons at the back. So we have, I just showed you two interfaces that are example of modularity. They work together. So this one works with to produce an inverse file, while the previous one uses the inverse file to do orbit correction with EPICS. It has been traditional, and it still is traditional for other labs. Well, I guess it's not controversial. All the other labs do it with these two interfaces tied together in one application, which makes it a lot difficult to handle these things. We've decided to separate the two interfaces because we have so many BPMs, so many correctors, they couldn't fit all in one window, even if the window had pages. So we can make configurations in advance, several of them, and then try one after the other using this interface. And we'd actually have a record of what we've done because each of these configurations are named and they're in the file system. And we always, we can do post-mortem from things that happened last year simply by looking at the data, the configuration data. There's a third example that I didn't show is the BPM status. Adam Brill may be familiar with it. The diagnostics group also are responsible in telling us which BPM have problems, not just physicists figuring it out by looking at the beam. They figure out which BPM has problems, and they decide whether they're good enough just for logging and nothing else, good for orbit correction, good for real-time feedback system. We have a separate interface for that, and that the file saved for the interface feeds into this one. So you notice some of the BPMs don't have a button even. That's because they don't exist. The diagnostics group have made sure that we never can press this button. So that's an example of inter-file communication or interface communication. Here's the interface that uses SDDS experiment and also communication control of a network analyzer, which is not in EPICS. Oh, yes, it is in EPICS. The waveform is in EPICS. But there's other examples where it's not, and RF frequency. So these are the parameters of the scan, how many points, what is the range of the RF frequency, how many points to take, and there's some processing buttons down at the bottom, and some options whether you want dispersion or chromaticity or both to be made. Here's a tickle knob for the storage ring tune. This interface looks the same whether you have tunes or orbit bumps or what have you. Ganged PVs would look like this. You don't actually directly see them. The first part here is one knob. It's called Tune X. We have to give it a name. It has arrows, and when you click an arrow, it will change all the PVs that is represented here by some amount determined by the gain here. If you want to read the list of PVs, press info and you get the SDDS file printed out in a separate window. This interfaces can be configured for, like I said, tunes, skew quadrupole harmonics, orbit bumps. Yes, those are the recent ones I used. It could be used for any arbitrary set of PVs that are related in some way. These knobs can also be used in SDDS experiment. This is a file. The knobs are defined by file. That means you can evoke this knob from an experiment designer or other tickle application. I included this because it has complicated a widget to display 3,000 sampling data points. We have, as of 3 years ago, we have complex BPMs that are extremely flexible in the way they're triggered. the BPM can read, the electronics can read what the BPM sees in RF signal at a time slot of 11 nanoseconds times something like 4,000, approximately 4,000 time slots, and then it repeats. So what the IOCs of this BPM requires is an array of 4,000 values of either on or off sampling. It also needs whether it's going to be triggering an X plane or Y plane, or selecting a phased, what is it called, a phase commutator or not. And we have to be able to configure it. We have to be able to time these BPMs. So we have up here what the sample configuration would be. Here we have 24 bunch pattern, but we only read, say, 20 bunches. There's a big gap here because the switch are slow and the data is invalid while we switch between planes. So this is how the BPMs are controlled. We can actually change values in this interface and make an SDDS file, which would then be sent over to the IOC. The IOC is made, we can use the SDDS file to send a waveform to the IOC. And here's some data that would help guide the diagnostic group person on where to put this gap, for example. Okay, so that is it. Obviously, I explained maybe a little too many applications, but it was really to give what can we do with the EPICS. Most of the talk was really what we can do with TCL and EPICS. Without going too much detail, I gave you some syntax of TCL, TK, and some of the syntax of some of our libraries that we use. I didn't go too much in the SDDS tool arguments. I know there's 100 tools available, and it would take a separate lecture to go over the function of each SDDS. I didn't start because if I start, I'm going to have to go a long time. So the SDDS file protocol is simply used to manipulate the data between EPICS and the file system. I can say that we've been using tcltk since 1995. We could have used others. Other scripting languages are just as fine. I went to NSLS2 last November, and they're using Python. And I was able to use SDDS toolkit, which was installed there, along with Python, in the same way tcltk was being used with SDDS. Other labs use MATLAB in a role of tcltk. So instead of launching, they don't actually use SDDS toolkit. They just simply use MATLAB functions to do processing and such, because MATLAB can do arrays and operations on arrays, which is what SDDS toolkit does mostly too. It operates on columns and rows like a MATLAB function. I would say SDDS toolkit is more flexible because they're pieces and you can join them in any way you want. By the way, MATLAB does have an SDDS extension, so if you want to write to SDDS, you can do so in MATLAB. And I believe we did the same too in Python. Bob Soliday is keeping up with that.